Right.
Okay, today we move on to the next section. Next section. There's only 3 sections now. So what are we learning today? Compounded interest. Some graphs. Oh, we gotta be able to do graphing. All right. So let's take a look at some formulas. Oh, let me teach you something first. So remember yesterday? What is the limit as n approaches infinity of 1 plus 1 over n to the n? E, it's E, that's how you get the number E. But this is just a special case of a more general formula that you need to know. The limit as n approaches infinity of 1 plus box over n to the n is e to the box. This is a more useful formula. Can you see that this is just a special case when x is 1? So the number that's here, whatever number is here, that's the power of e. And that's what you're going to have to do in tonight's homework. And then I'm going to give you, okay, let's start off easy then. What is the limit as n approaches infinity of 1 plus 3 over n to the nth power? If I plug in bigger and bigger numbers for n, 100, 1,000, 1,000,000, 1,000,000,000, 1,000,000,000,000, it's going to get closer and closer to what number? E to the third. Whatever number is there, that's the power of e. Isn't that pretty easy? Now, do you think you're going to get that though in this class? No. See, in pre-cal regular, then you get that. This is the kind we get in this class. What is the limit as n approaches infinity of n minus, that's not n, n minus 2 over n to the nth power? Okay, now some of you can see it. So what you have to do is you have to make this look like this. So what you got to do is you got to massage it. You got to low me it until it looks like this. Okay, so what can I do? Okay, well, did you guys learn this in Algebra 1? A plus B over C is equal to A over C plus B over C. You know, what is this technique called? It's called lift and separate. So, if I lift and separate, n over n is 1 minus 2 over n to the n. Hey, Mr. Park, it's starting to look like this now. Lifting and separating, that's an important technique in calculus, you know. But Mr. Park, that's a plus sign, so how can I change this to a plus sign? Put the negative over there. And then now, doesn't this look like that? So if I plug in bigger and bigger numbers for n, what is it going to get closer to? E to the negative 2. Okay, at least you had to do something there, but even this one is tame. Okay, are we ready for the one that you're going to get? What is the limit as n approaches infinity of n over n minus 3 to the 2n power? How can I make this look like this? Can I lift and separate? Can I lower and separate? Because that's what some people wanted to do last year. So this is true, but if you have a over b plus c, is that the same thing as a over b plus a over c? Don't you dare do this. This is a triple fatal error on the test. Look, just try numbers. Is 5 over 2 plus 3, what is that equal to? 1, right? Can I do this? 5 over 2 plus 5 over 3. So is 1 equal to 2.5 plus 1 2/3? I don't think so. No, so I can't. What do I do, Mr. Park? Well, now you got a huli. Is there a way I can flip it over like this? You guys know what huli is, right? Huli chicken. They keep flipping it. Because look, like over here, if it's like this, I can lift and separate, but like that cannot. So you huli it. Can I? Is that legal? No. Yes, if you put the negative in the exponent, right? Because negative means flip it over, right? -1 power. So this is what I mean about you got a huli, you got a lomi. Okay, now lift and separate. 1 minus 3 over n, but we already know from the previous problem. Make that a plus and put the negative with the 3, right? Yeah, but wait, Mr. Park. I just need an nth power there. That's -2n. I just need n. So again, you massage it. Can I just put an n like that? Yeah, if you put the -2 outside the bracket, because then you multiply the exponents, right? Okay, so just look at what's inside the brackets. What is the limit of this? 1 plus box over n to the nth power. If you take the limit as n approaches infinity, it's going to get closer and closer to e to the -3. So the thing in the brackets gets closer and closer to e to the -3. Therefore, the whole thing will get closer to e to the -3 to the -2, which is e to the 6. That's your answer. That's pre-calculus honor level. In fact, BC calculus. Well, that's what I'm training you for next year, right? BC calculus. I'm not training you to go to AB, even though some of you are going to take AB next year. We're training for BC. All right. So now, where have you seen this formula before? Not continuous, just regular compounding interest, right? So let's define everything. What is P? Your principal. How much money is your initial investment? Remember, whenever you have an exponential function, that number there is your initial amount. What is R? Your interest rate. N. How many times you compound interest per year. So if a bank says, well, we compound interest quarterly, so what would N be? Okay, what about daily? 365. What about secondly? Okay, forget the secondly. How about, what about minutely? Have you guys ever seen rent? There you go. You guys never saw rent? 525,600 minutes. Okay, then just multiply it out then. Anyway, N is how many times you compound interest per year. Most banks will do it like quarterly. Some banks try to lure you, so they say, oh, we compounded monthly. So N would be 12. But as you know, there's a limiting value, right? So that's why it's only a matter of cents, yeah? And of course, T is the time that you leave it in the account, in years. Okay, I don't have to do an example for this, right? Okay, but what if somebody said, you know what? Our bank, we compound interest continuously. Do you remember that word from last year, continuously? That means you compound interest an infinite number of times per year. So what happens? Well, what would happen if you take the limit as n approaches infinity of this formula? What happens as the number of times you compound interest gets bigger and bigger and bigger? We're going to compound interest 5 billion times a year, or 75 trillion. Well, let's lomi it. See how I massaged it? Look in the brackets. What is 1 plus box over n to the n? And then you take the limit as n approaches infinity. What did we just learn 1 minute ago? E to the box. So as n approaches infinity, this thing in the brackets gets closer and closer to e to the r, right? Therefore, the whole thing gets closer to P, e to the r, and then you multiply the exponents. And then you guys, of course, remember this formula, yeah? See, but last year, you guys just memorized it. Now we know how we got it now. You take the limit as the number of times you compound interest goes to infinity. So you gotta make sure you know when to use which one now, because on the test, you gotta know both of these. I'm not sure if we're gonna have a test on this yet, but this is for compounding interest a finite number of times per year. This is when you compound interest continuously. That's like an infinite number of times a year. Just make sure you know when, it's pretty obvious there. Okay, the next thing is your base graphs. Let's go over. There's only 2 base graphs you gotta know on tonight's homework. The first one is y equal e to the x. So for graphing purposes, just know e is 2.7. That would be good enough. Now, last year when you drew graphs, how many points did you have to plot for this? Most algebra teachers make you plot 3 points, yeah? -1, 0, and 1, right? So let's do it. -1, 0, and 1. Okay, plug in. Okay, let's plug in the easy one first. Plug in 0. E to the 0 is 1. Okay, what happens when you plug in 1? E to the 1. 2.7. Good enough. 2.7 is good enough. Okay, what about -1? E to the -1 is 1 over e. Anybody? Come on, you guys did it last year. Okay, I'll tell you, 1 over e is approximately 0.367. There's certain numbers, you know, when you see it in math, and you just know. Like, 1 over e is approximately 0.367. And then for those of you in chemistry, doing half-lives and things. Natural log 2, anybody? 0.693. Mr. Park, we just use our calculator. Okay, what about square root of 2? For trigonometry, when we start graphing that, 1.414. What about square root of 3? 1.732. Okay, whatever. Just anyway, 0.367. That's about there. Connect the dots. And there's your graph. That's what a typical exponential function looks like if the base here is greater than 1. What would happen if the base here is smaller than 1? Like what if you had 0.4 to the x power?
Oh, it'd be getting closer to
Yeah,
0.
then the graph would go down like this. See, so when this base is bigger than 1, you get exponential growth. But if the base is between 0 and 1, then you get exponential decay. You guys are looking like, did we learn this last year? All right, now what if I told you graph the inverse of this? Remember all that stuff we did in functions? We're going to do it again. How do you graph the inverse of this? How do you graph the inverse of anything? You switch the x's and y's. Okay, this was the point 0, 1. So if you switch it, you get 1, 0. Okay, this was the point 1e. So switch it. E1, so 2.71. This was -1 e to the -1. So if you switch it, you get e to the -1, which is about 0.367, and then -1. Connect the dots. That's the inverse. And again, look, hey, they're symmetric about the line y equal x. It always is. But what is the equation of this inverse? This is the important thing. Well, how do you get the equation of the inverse? You switch the x's and y's. So if I switch the x's and y's, you get x equal e to the y. But how do you solve for y? Well, you can't do it algebraically, so somebody had to invent notation for this, which you guys learned last year. Okay, now some of you are going, well, I forgot everything. Okay, let's just go back even further then. When you first learned logarithms last year, like that, what does that mean? This is called logarithmic form. How do you change something from logarithmic form to exponential form? B to the C
Equals A.
equals A. And I'm sure your teacher told you if you just go back and forth between these two, right? Doesn't it make it really easy? Okay, so this is exponential form. This is like this. Change it to logarithmic form. How do you change this into logarithmic form? Y equals, you got to be able to go from here to here. That's what we're doing. We're going from here to here. Y equals log base E of x. But last year, what did we learn? Log base E is, we don't call it log base E, we call it natural log x. What happens if it's base 10? Then we just go log, right? So if you have log x and there's no base there, that means log base 10 of x. But I'm going to tell you in calculus, everything we do is natural logs. Everything. So just get into the habit of doing natural logs only. In fact, on the test, well, if we have a test or on the quiz, if I ask for an answer, I'm going to say write your answer using natural logs. So you're going to have to do it. Oh, so Mr. Park, I get it now. A logarithm is simply the inverse of an exponential function then. Exactly, that's exactly what it is. And if this and this are inverses of each other, what did we learn when we studied functions? What would happen if you plug one into the other? You get x. And that works for anything. If you have two functions that are inverses of each other, if you plug one into the other, it doesn't matter which way, you will get x. So if I take this and plug it in here, you get x. You guys probably learned it like this. See, y equal b to the x, y equal log b of x. These are inverses of each other. So if you plug this into that or that into that, you get x. But we're only going to do natural log. Okay? So that's why we just do it like this. So if I plug this into this, you get x. If I plug this into this, natural log of e to the x, you also get x. See how important it is? I boxed it. If I box it, it must be important. And this just comes from the fact that they're inverses of each other. Okay, so for example, some of the problems on tonight's homework. What is e to the natural log 7? Here, I'll give you a hint. Look at this. 7. What is the natural log of e to the 4? 4. That comes from this. That's because they're inverses of each other. Anyway, so these are the two base graphs you need to know. What you're going to do is you're going to do things to them. Okay, I'll just do one example. Because you guys should be experts at, reflecting. It's not that easy, when you get old. Okay, here, which one do we want to do? Let's do natural log. No, you know what? I'm going to do two graphs. How about e to the negative x, 2 minus, okay, here. Draw this graph. What's the base graph? E to the x is the base graph, so plot the points. Now, actually in calculus, by the time you get to calculus already, you really only need to plot 1 point right there, 0, 1. That's good enough. And then you know the graph looks like this, right? Right? In fact, for me, if you just simply plot the point 0, 1, you don't need these two other points. You usually only do that in algebra 2, but every time you move up the ladder, you're supposed to remember things. So that's good enough for me, 0, 1. Okay, now what does this do to the graph? Reflect it over the 50-50 chance, x-axis or y-axis? Y, the y-axis. You reflect it over the y-axis. What does that do? That reflects it over the x-axis. So now the graph looks like that. Yeah, but Mr. Park, if I switched them, I would get it right? Yeah, you would, but then of course, you know what's gonna happen. I'm only gonna give you, I'm gonna give you things where it's, like if you do the wrong thing, you're not gonna get the right answer. And then finally, what does that do to the graph? Shift it up. So this graph right here gotta be shifted 2 up. Everything gets shifted 2 up. So this y-intercept gets shifted 2 up. But then look, this is an asymptote. I hope you guys noticed that. Exponential functions, the x-axis is a horizontal asymptote. But in a logarithmic function, the y-axis is a vertical asymptote. That's because we switched the x's and y's. So this is an asymptote. That asymptote also has to get shifted 2 units up. So what does the graph look like? Yeah. That's how you draw the graph. Okay, we gotta do one more. Should I leave that on, or you guys know? You guys know. Okay, y equals, let's do a natural log. Natural log, x minus 1, now let's do x plus 1, absolute value only on the x. Okay, what's the base graph? Natural log x. So what's the point you gotta know? Well, if it's 0, 1 for e to the x, then for a natural log, 1, 0, and then. Okay, now there's 2 things going on here. This one will shift it 1 to the left, but then this thing here, remember, erase everything to the left of the y-axis, keep and reflect? Which one do you do first, because it matters? Shift first, or do the absolute value of x thing first, and then shift it?
Shift.
Huh? Shift first, or absolute value first?
Shift.
Very good. And if you don't know, figure it out. Okay, what if you did the absolute, okay, here's the base graph. What if you did the absolute value thing first, and then you shifted 1 to the left? Well, how do you shift the graph 1 to the left? You substitute x plus 1 for x. If I substitute x plus 1 for x, is that what it is? No, so that's why it's wrong. Don't guess, figure it out. So what if I take the base graph, shift it 1 to the left first, and then do the absolute value thing? Yep, that's what we want to do. So shift the graph 1 to the left, that means this point comes here. This asymptote is here now. And remember, every year students lose points because they don't draw the asymptotes. Anytime you have a graph with an asymptote, you gotta show it with a dotted line. Okay, so now the graph looks like this. Okay, now apply the absolute value. So this is what the graph is right here now. How do you apply the absolute value thing to it? Erase everything to the left of the y-axis, so this, and then you keep and reflect that about the y-axis. Boom, that's the graph. And we're going to keep doing this. When we get trig functions, you're going to do the same thing. We get inverse trig functions, same thing. Do not purge these. I guess you can purge it if you want, but then you're going to have a hard time in calculus. Because the hardest thing in calculus is not the calculus. The calculus theorems are easy to follow. They're just rules. The hard things are the pre-calculus things, like making number lines, drawing base graphs, using properties of logarithms, using trig identities. Okay, so there's a whole bunch of graphs you're going to have to draw. Now, what about these other things? Mr. Park, look at number 2. These are 4 very important graphs in mathematics. Have you guys ever heard of the hyperbolic trig functions? Mr. Park, I barely know the regular trig functions. Okay, I'll do one of them for you. Okay? See, when you have a cosine with an h there, that means it's hyperbolic. Usually engineers, this comes up in engineering and physics. This is the definition of the hyperbolic cosine function. I told it to you right there. Now, just by knowing the graph of e to the x, can you draw this? Well, just ask yourself, do you know how to graph this? Yeah, I just showed you. What about this? Yeah, that just reflects it over the y-axis. And what happens when you add 2 things and divide by 2? What is that? Finding the average, right? So I think we can graph this by hand. Okay, let me show you how we do it by hand. So here's the point 0, 1. E to the x looks like this, right? Correct? E to the negative x reflects it over the y-axis, so it looks like this. Now you take the average of the two graphs. How do you take the average of two things? What's the average of 10 and 20? 15. How did you get? Just go halfway in between, right? That's how you find the average of two things. So like right here, both y coordinates are 1. So the average of 1 and 1 is 1. So that's a point on the graph. Now for the other ones, you know what a good trick is? Just draw a vertical line, bisect it. Isn't that point halfway in between? Yeah, so for every, here's another one. Draw a segment, bisect it. Because that's halfway in between. That's how you find the average. So on this side, do the same thing too. Draw a segment, just go halfway in between. If you want more points, there, you want more points, do it. Connect the dots. There you go. That's what the hyperbolic cosine function looks like. Now, what I'm going to do though is I'm going to let you guys use your calculator for this. But ultimately, like if you're going to study engineering or physics, you got to know these graphs. Okay, so you can use your calculator for number 2, because before I used to do no calculator. Okay, how many of you are in AP statistics? You guys learned the bell curve? What's a bell curve? Okay, you know what? I'm going to draw it for you. Well, why am I doing your homework for you? Okay, this is not quite the same one you do in AP statistics, but this is a really important graph. Okay, let's just plot points. Well, you know what? Like if you plug in 0, you get 1, right? Well, what happens when you plug in bigger and bigger numbers for x? Like what happens when you plug in 1? You get e to the negative 1, which I told you is 0.367. What happens when you plug in 2? You get e to the negative 4. It's even smaller. What happens when you plug in 3? E to the negative 9. Well, so what's happening is the graph gets closer and closer to 0, and isn't this an even function? If you plug in negative x for x, you get the same thing. So the graph should be symmetric about the y-axis. See how it looks like a bell? A bell curve. Now you guys in statistics, you guys were taught that the area is 1. But you have to put a coefficient over here, I'll just call it k, in order to make it 1. Because without this coefficient there, if you just go negative x squared, this area is actually the square root of pi. It is not 1. So by toying with this coefficient over here, then you can make it 1, and that's the graph that they use in AP statistics. And number 4, the fourth problem. Can somebody read it to me? Or do I have to go there and look? I have bad eyes, you know. 3 over, can somebody read it to me? 1 plus something. What? Negative what? 0.9. Okay, so, okay. Now, where's my exponential growth equation? So here's exponential growth, exponential function. Now, in real life, do populations actually grow like this? Well, maybe for a while they do, but in real life, because of resources, predators, and things like that, populations don't really grow like this. They grow like this. So it might be exponential for a while, but because of like lack of resources or predators, then the thing starts leveling off. And it approaches an asymptote. That's what this graph is. This is called did you guys learn logistic growth when you took biology? Mm-hmm. Oh, there you go. And did you guys draw the graph? Oh, whatever. Okay, so these are all very famous graphs, important graphs in mathematics, so that's why I put them there. But you can use your calculator. You don't have to graph it by hand like I did here. Oh, by the way, let me ask you a question. I just want to see how good your physics intuition is. Let's say you have 2 points. I don't know, maybe you put up 2 poles or something. And then you let a rope or a chain just hang under the influence of gravity. What is the shape of that? Is it a parabola? No, it's not. Do you guys think, I hope you guys don't think any U-shaped thing is a parabola. Then that's the same thing as saying any animal with 4 legs is a dog. Just because it's U-shaped doesn't mean that it's a parabola. A parabola has to have a certain equation, and you guys should know what that equation is because we studied it and it's on the SAT, right? A parabola has to have this equation. So let me tell you, if you hang a rope or a chain under or a string under the influence of gravity, that is a hyperbolic cosine function. You can impress your physics teacher with that. In fact, have you ever heard of this state called Missouri? And then there's a city in it called St. Louis. And in St. Louis, they have this arch. What is it called? The Gateway to the West or something? The Gateway Arch. Come on, help me out here. Mr. Parker, never even heard of St. Louis. Well, what is that shape, you think? I would bet a lot of money that a lot of people go there and go, hey, look at that parabola. Just shake your head with people. This is an upside down hyperbolic cosine function. That's what it is, because it comes up in nature so often. In fact, another name for a hyperbolic cosine function is a catenary. Now, I'm telling you guys these things so that when you take physics or if you go to college, then you don't want to get laughed out of the dormitory, do you? Just like if you go to college and you start saying Euler, you're going to be laughed out of the dormitories. In fact, a former student just emailed me. She's at USC. She said she took a class and the professor said Euler. And then the class started laughing. And he goes, what are you laughing about? Well, you said Euler. It's not Euler, it's Euler. And the professor said, well, that's the way I learned it, and I'm going to keep saying that. Anyway, so my former student said that's the definite strike one, and I said, yes, that's strike 3, in fact. Okay, what are the other things you got to know for tonight's homework? Okay, so this is all simple stuff. This is like algebra 2 level right here. Okay, for example, let's do some log ones. What is log base 2 of 8? Okay, some people can just look at it and see it. So some of you are kind of out of shape, I don't know what this is called, I'm going to call it x. If you see something in logarithmic form and you don't know what to do, change it to exponential form. If something's in exponential form, change it to log form. So if I change this into exponential form, what do I get? 2 to the x equals 8. Now I think you can figure it out, right? 2 to the what power equal 8? 3. So the answer is 3. So this is 3. Okay, but after a while, you should just be able to look at this and go in your head. In your head, you should go 2 to the what power equal 8? 3. Okay, let's see if we can do it without putting the x there. Oh, shoot. Log, oh, that's a story right there in itself. You know the LG? I made a mistake there. We had she was in the class of 1989. She was on the math team. And for some reason, this is how she wrote logarithms, just so she can write less things. But she actually did it at a math meet. And of course, there's no such thing as LG, right? Well, in math anyway. So all her answers, she wrote LG, every problem wrong. So what are we talking about here? Log base 3 of 81. So in your head, you think, 3 to the what power is 81? 4. There you go. Log base 5 of 1 over 25. So 5 to the what power equals 1 over 25? -2. Okay, log base 16 of 4. 16 to the what power equals 4? 1/2, right? Because 1/2 means square root, right? So hopefully you can do these in your head. What about something like this? Let's see how good you are. log base 8 of 4. 8 to the what power is 4? Okay, some of you can do it, but see, it's not a whole number anymore, so now makes it harder, right? So maybe you want to go on the side and go 8 to the what power equal 4. Maybe if you have it written like that, you can see it. Okay, so this is like last night's homework then. How do you solve an equation like this? We did it on last night's homework. We had homework last night.
Same base.
Change it to a common base. 2. 8 is 2 to the third. 4 is 2 to the 2. Multiply the exponents. If 2 to the gorilla equals 2 to the banana, gorilla must equal banana, so x equals 2/3. Yeah, you can do that, but hopefully you can do it in your head. So you know the common base here. Let me show you how to do it. 2 is the common base, right? So to get from 8 to 2, what do you have to do? You got to cube root it. That's the 1/3. And then to get from 2 to 4, you got to square it, and that's where the 2 comes from. Okay, let's do a couple more. What time is it? Okay. Log base 27 of 81. So in your head, you're thinking, okay, 27 to the what power equal 81? I don't know, Mr. Park, it's a fraction, that's why. Well, what's the common base? 3. Okay, how do you get from 27 to 3? You cube root it, so that's 1/3 power, right? And then how do you get from 3 up to 81? You raise it to the 4th power. There, 4/3 power. Okay, and like I said, if you can't do it in your head, don't worry. Just do this. 27 to the what power equal 81. 3 to the third, 3 to the fourth, 3 to the gorilla equal 3 to the banana. So gorilla equal banana, so x equals 4/3. There's nothing wrong with doing that. Just takes a little bit longer. Okay, last thing. F of x is equal to 2e to the 3x plus 4 plus 5. Find f inverse. How do you find the inverse of anything? Switch to x's and y's and solve for y, right? We just did that in functions, but now we get new functions now. So think of this as y. Switch to x's and y's. Okay, but now you got to solve for y. How do I solve for y? What should I do first? Subtract the 5. Hopefully you can do multiple steps at once. Subtract the 5 and then divide by 2. Okay, very good. Now, once you isolate the e here, how do you get rid of the e? Yeah, change it into logarithmic form. That's what you were taught last year, right? Or, here's a different, so yes, you can change it to logarithmic form if that's the way you've been doing it all along. But did your teacher teach you just natural log both sides? Okay, watch. If you want to get rid of an e, you natural log both sides. Now, why do you do that? Because what is the natural log of e to the gorilla? Gorilla! Because they're inverses of each other. So to get rid of the e, you natural log both sides. It's just a different way of thinking about it. If you don't like what I'm telling you, then just change it to logarithmic form. It's the same thing. And then now, isn't it easy to solve for y? How would you solve for y? Subtract the 4. And then divide by 3. Boom! Okay, let me show you one more thing, and then we'll be done. F of x, let's do a logarithmic function now. 3, natural log, 2x plus 5 minus 4. Find the inverse of this. Okay, so think of this as y. How do you find inverse again? Switch the x's and y's. And then solve for y. So what do I do first? Add 4 to both sides and then, okay, so add 4 to both sides and then divide by 3. Now, if you want to get rid of the natural log, you can just change it to exponential form because that's like an e here, right? So you can go e to the this equal that, okay? Nothing wrong with that, but this is just a different way of thinking about it. Well, if I want to get rid of an e, we natural log both sides, right? So what do you think I'm going to do if I want to get rid of a natural log? You e both sides. So if gorilla equal banana, then shouldn't e to the gorilla equal e to the banana? Okay, so what do we have? We have e to the x plus 4 over 3 equals, what is e to the natural log banana? Banana. But think about it, isn't that just the same thing as going e to the this equal that? It's just a different way of thinking about it. It's up to you what you want to do. And then how do you solve for y? Subtract 5 and then divide by 2. So y equals e to the x plus 4 over 3 minus 5 and then divide by 2. Boom, that's the inverse. So every single function we're going to come across, you have to be able to find the inverse. Even when we do trig functions next chapter, you're going to have to find the inverse. In fact, do you guys remember anything about the inverse trig functions? Mr. Perk, don't worry about that when we get there. All right, so look, we're not even using properties of logarithms yet. That's the next lesson, which is, well, we have a holiday on Monday, so on Tuesday. Yep, so we're not going to even learn the properties of logarithms till Tuesday. That's when we get the really good problems. So right now, not that bad. It seems like you guys remember some stuff, which is good. I hope trigonometry you guys remember. So what about the graphs? If you have to graph like cotangent x, could you? Not even plotting points. I guess we're starting from scratch then, huh? Okay, so we got 8 minutes left. I don't know. I'm not going to excuse you this early anyway, so why not try a couple problems? Or start studying for the rational test.